So today we are continuing on with thermophysics, having established the concept of temperature in our previous lecture. Today we just dove in more to look at how temperature also comes into play in affecting change in a system. So today we are mostly going to be concerned about gases. Today we're mostly going to talk about gases, how gases, behave. Not necessarily the chemical, behavior of gases, but the mechanical behavior of gases, and how its volume changes with pressure and temperature and whatnot. So we're going to look at gases in that way. So we are going to start with the concept of thermal equilibrium before we come to actually to talk about gases. But we just want to talk a little bit about thermal equilibrium, but we'll explore more about thermal equilibrium in the later section of the chapter on thermophysics. For now, we'll just have a highlight on thermal equilibrium so that we just get a picture just to have on the back of our minds. So when we talk about thermophysics, we talk about thermal. I'm sure you guys know or have heard of the word thermal, and the word thermal actually talks about it relates to heat and temperature and stuff. So we'll not go into details of defining what thermal means, but when you hear the word thermal, all right, when they talk about thermal energy, all right, then you know that there is heat involved in that production or in the generation of energy, or there's heat energy involved. So when we talk about thermal equilibrium, we talk about an equilibrium that has to do with temperature, all right? So heat flows from a hotter body to a cold body. I'm sure we know that, all right? So if there's a hot body, if you have hot cores, all right, and then you place a cold pot, a pot of water or so, you place it on a hot core or on a brazier, you expect the heat from the brazier to start transferring from the brazier to the cold pot. So we know that thermal equilibrium, for thermal equilibrium to be established, we have to have heat flowing from a hot body to a cold body, to a colder body, all right? So from a hot body to a colder body, we have heat flowing in that direction, all right? So heat can only flow from a hot body to a cold body if they are in what is called a thermal contact, all right? If you have one body like this, all right, you place it in a thermal contact with another body, all right? And then we call this one body A, and this other one body B, where if body A is hotter than body B, if body B is cold, we expect heat to flow in that direction, all right? It will continue flowing in that direction over some time until body B and body A become in a place or in a condition called thermal equilibrium, all right? If they are in thermal contact, all right, they may not necessarily be physically contact. They may even be spaced by a medium. For example, you place two objects in a container where there's gas. You find that gas will be a medium which will transfer heat from one body to the other, and eventually the two bodies will be in thermal equilibrium. So what the idea is here, for heat to flow from one body, from a hotter body to a colder body, we expect the two substances to be in thermal contact. Even if they are spaced like this, one body is here and one body is there. But if there's a surrounding media which can transfer heat, all right, like that, maybe water or gas or anything, we'll find that heat will move from this body to the other body, like that, until eventually these two bodies, body A and body B, will eventually have the same temperature. So when the two bodies in thermal contact have the same temperature, so eventually, if two bodies are placed in a thermal contact, they'll have the same temperature eventually. And this having of thermal temperature is what this having same, this word, same temperature. If two objects which are in thermal contact have the same temperature, we call it thermal equilibrium. All right, object or system. So if you have an object or a system that has the same temperature, we call it that it is in thermal equilibrium with each other. All right, all right. So this, as we will see in other sections, we will see that this is the zeroth law of thermodynamics. All right, how many of you guys have ever heard of the word thermodynamics? Thermodynamics, anyone who has ever heard of the word thermodynamics? All right, we have not heard of the word thermodynamics. Kalma, have you ever heard of the word thermodynamics, the term?
I have.
Yeah, yeah, I was asking, has anyone ever heard of the word thermodynamics? I was hoping to hear a response. Yeah, so thermodynamics, actually from the word thermo, already you can also hear that thermo is talking about heat, and dynamics, the movement of heat. So from the zeroth law, I'm sure you know about first law of Newton, second law of Newton, because Newton is the one who came up with those laws. There's also now the person who came up with these laws, his name is not thermodynamics. All right, these laws are just called laws of thermodynamics, just like the way the laws of Newton are called laws of motion. First law of motion, second law of motion. Here now we also talk about, here now, in fact, instead of starting with the first law, we start with the zeroth law. So we start from zeroth law to the first law, the second law, like that. So now the first law of thermodynamics is the one, not the first, but the zeroth law is the one which tells us that heat should be able to move from the colder body to a hotter body. All right, it's a principle like that. So you don't expect heat. For example, if you have ice cream, for example, it might be at 0 degrees, and maybe you have water which is at 100 degrees. You don't expect ice cream to get some of its temperature and add to the heat of water. All right. So we expect that water which is at a higher temperature should be able to add heat to the colder ice cream. So heat should flow from a hotter body to a colder body. And this is what is called the zeroth law of thermodynamics. You will encounter this concept more often if, for example, you go into the branch of engineering, you will encounter with this. But if you go in medicine, this might be the last time you're hearing it. All right, so if you want to hear it, don't go to medicine. Okay, so two bodies. This is what the zeroth law of thermodynamics say. It says two bodies, all right, two bodies or systems that are in thermal equilibrium with a third. Now, this is what the zeroth law of the thermodynamics say. If you have two bodies, or a system that is in thermoequilibrium with a third body. All right. So you have one body like that is in equilibrium with one body like that, with another body. If body A and body B are in thermoequilibrium, but also if body B and body C, we have another body like that, body C. If body B is in thermoequilibrium with body C, meaning body C should also be in thermoequilibrium with body A. So it looks simple, but actually this required a lot of science to come up with this law. So if this is in thermoequilibrium with that one, and this is in thermoequilibrium with that one, we expect that this should also be in thermoequilibrium with that one. All right. So if two bodies or a system that are in thermoequilibrium with a third body, two bodies or system that are in thermoequilibrium with a third body are in thermoequilibrium with each other. So we expect that body A and body B and body C to be all in thermoequilibrium. What does thermoequilibrium mean? Thermoequilibrium means same temperature. If they have the same temperature, meaning they are in thermoequilibrium. So if I have 25, if my temperature is 37 degrees and Sante's temperature is 37 degrees, then we are in thermoequilibrium, all right? Because we have the same temperature, all right? If it happens that Simbarashe also has 37 degrees, meaning Simbarashe and me and Sante are all in thermoequilibrium. I hope it's clear that far. Are we okay that far? Are we following?
Yes.
All right. Okay. I hope you are all following. So if you have any question, you are free to interrupt me. So I just wanted us to just look at this concept a bit, and then we'll move over to the main concentration of our study this morning. But this will come to it at a later stage. All right. So this is just what it's talking about, which I say that this diagram. So if body A is in thermoequilibrium with body C, and body B is in thermoequilibrium with body C, then body A is in thermoequilibrium with body B. So if this is in thermoequilibrium with that one, and if that is in thermoequilibrium with that one, then we also expect that this should be in thermoequilibrium, like that. So, like I said, this concept, we'll get back to it later. I've talked about it now because in your notes, which they send you, they are there. So maybe they might ask a question in the multiple choice quiz that you have on this topic. I don't know. So it's just good for you to have it at the back of your mind. But otherwise, our main concentration is to talk about the ideal gas law. We have to talk about gases, all right? So our main concentration is to talk about the gas law. And so we know that gas, anyone who can tell us the definition of air? Okay. Usually we define air as the mixture of gases, right? In air, we have oxygen, carbon dioxide, nitrogen, and all that kind of stuff. So one thing that you discover is that when we come to physics, oxygen and hydrogen behave the same way, all right? Nitrogen and carbon and whatnot, as long as it is a gas, when we come to physics, they behave the same way, including water vapor. Water vapor is also a gas. You discover that water vapor and hydrogen and oxygen, they will behave in the same way, because we usually in physics, we talk about their mechanical properties. All right, we talk about their mechanical properties, but in chemistry, you will talk about their chemical properties. You know that chemical properties are, attributed to a gas due to its, valency and, its ability to how it reacts with other chemicals. But for us, when we talk about gases in physics we talk about their make properties. So I'll just abbreviate it as MEC. So we talk about their mechanical properties. Now, so when we talk about the mechanical properties of gases, we'll talk about their pressure and their temperature. All right. Not only are we going to talk about pressure and temperature, also talk about their volumes. All right. Volume, temperature, and pressure. Okay, so we have Precious who has also joined us, or she's still joining. Yeah. So like I said, feel free to always ask whenever you are not clear. So the three variables that we've talked about, pressure, temperature, and volume, enter into the gas law. All right. So let us try and look at the first premise. The first premise that we're going to look at is, we have these three variables, right? Three variables. If you have a gas in a container like that, all right, you have gas in a container like that, all right? So if this container is tied fully like this, such that this container cannot expand or contract, we expect that the volume is what? Is fixed. All right. Volume is fixed. So I want us to talk about the first premise is where we talk about the volume being fixed. So yeah, we have Precious who has joined us. She's still joining, but yeah, hope she gets to catch up. So we have talked about these variables: pressure, temperature, and volume. But then when we describe the gas law, all right, the ideal gas law, we need to go step by step. So we can't talk about all these variables at the same time. We must eliminate one of them at a time. So at this point in time, we're going to eliminate volume by making volume constant. So we just look at, so that we can look at pressure and temperature, how it interacts with a gas mechanically. So if a gas is confined to a fixed what? Fixed volume, and it is heated, all right, its pressure will do what? Will increase. So if we have a fixed volume like that, and then we introduce some fire, all right, some fire. All right, let me use a red, yeah. So we introduce some fire there. What do we expect with the pressure here? What we expect with the pressure here is there'll be so much pressure, all right, such that these gases will be moving at a faster rate, hitting the wall of this container and producing a lot of pressure in this container, because we have done what? We have increased temperature. We have increased. If we heat it up, when we heat it up, what happens? Temperature increases. And when temperature increases, also pressure increases. Okay? So, we have Precious who has joined us. Precious, good to have you. You have not turned on your mic. You can't hear us. Precious. Okay. Just a moment. Okay. Just a moment. Just give me a moment. I help our friend. Just a moment. Okay, so there's a friend of ours who has joined in by the name of Okay. So maybe you could help us identify you, Mr. or Mrs. Okay, the one who's written Okay. Who might you be, so that we can. Anyway, maybe we don't want to waste so much time in identifying people because we are running out of time. So, to our friends who have joined us recently, we are talking about ideal gases. We have already talked about a few things, which you can be able to follow up when you watch the video, the remaining part. So here now on the ideal gases, we are talking about the mechanical properties of gases when in terms of pressure, temperature, and volume. So we are going to look at these three variables today, and we just want to see how they interact with each other when one variable is increased or decreased and whatnot. So to talk about these variables efficiently and effectively, let us try and eliminate one variable at a time. So in the first premise, we have removed volume out of the equation because we have said we want to talk about fixed volume. So when we have fixed volume, we introduce heat, we increase the temperature, we expect the pressure to increase. And this increase is linearly, it's a linear relationship. So a linear relationship is established like this. So if I increase my temperature like that, imagine this is my temperature and this is my pressure. All right. So if I increase my temperature like that, I expect my pressure to also be increasing. So they have a linear relationship. And so this linear relationship is established mathematically like this. When you see this sign, it's talking about proportionality. So it tells us that pressure is proportional to temperature. When what? When volume is constant. All right. So it means that if we increase pressure, temperature will also increase. All right. So with this mathematical expression, we can come up with this other equation down here. This equation talks about what happens if you have a pressure 1. All right. If you have a pressure 1, and then you discover that at a certain point, the pressure increase goes to pressure T. Now this pressure 1 was at a temperature, at a certain initial temperature. When you increase the temperature, you discover that the pressure also has increased, but to a certain value that you don't know. So you can use this relationship to help you know any unknown in this sequence by understanding that pressure and temperature are related to each other like that. So if you have a pressure 1 and a temperature 1 should be equal to any pressure and any temperature at any point in time, given that the volume has been fixed. So if you fix volume by putting a container that cannot expand or contract like that, you can determine the pressure at any temperature if you know the initial condition. If you know the pressure 1 and the temperature 1, you can be able to know if the pressure changes, you can know what temperature it has. All right. So this is the first premise where we have put our volume constant. Are we okay that far? We are going to look at some examples later on, but right now we just want to establish a few things. Are we okay this far?
Yes.
Okay. I've seen some of our friends have, I don't know, have disappeared. Precious, you finally managed to join in audio because earlier on, your audio was not on.
Yes, I managed.
Awesome. Okay. Good to have you. Hope you are doing fine.
Thank you. I hope you're fine too.
Awesome. I'm fine. Yeah. So, yeah, we continue on. In the first premise, we had put our volume constant. And the second premise, what we are going to do is we are going to put pressure constant. Remember, we are talking about these three variables: pressure, temperature, and volume. And we want to see how they interact with each other. When we change one, what happens to the other? So in the first premise, we first put volume to be constant. So we removed volume out of the equation. But in this second premise, we are going to remove pressure out of the equation. How do we remove pressure out of the equation? By putting pressure to be constant. So if the pressure is kept constant, a sample of gas expands its volume linearly with temperature. All right. So what happens is this case. If you have a cylinder, for example, in an engine like that, you put a stroke that way, a stroke that way, like that. You allow it free to move along these edges. All right. So here you have a gas. All right. You have a gas. If you get to introduce some heat here, right? Some heat, right? If you increase the temperature, what will happen? You discover that the volume will increase. So if this was volume 1, when you increase the temperature, the volume will go to volume 2. This stroke will be moved upward by an introduction of heat. So when we keep pressure constant is we allow this stroke to be freely movable, to be able to move, so that when we introduce heat, we discover that this stroke can move freely upward or downward. If we remove heat, it will move downward like that. So this happens when pressure is constant. Our volume changes with temperature change. Volume is proportional to temperature. In this, we can further write out like this. All right, we can further write it out like that by telling us that if we know the volume at initial stage, all right, if like the same diagram which I had drawn is this way, all right, and then we have a stroke like that. So if we know the volume 1 and the temperature at that point, temperature 1, if we increase the temperature to a temperature 2, and we discover that the volume has gone to level 2, we can compute it by knowing that the condition that I had on volume 1 and temperature 1 should be equal to the condition that were on volume 2 and temperature 2. By this expression, you can be able to find any variable in that expression. Now, this is only when pressure is constant, all right? So we put it as constant. Now, so this is what we have established so far by looking at temperature and pressure, all right? So we go back to our asserting that an ideal gas behaves in such a way that we'll have variables pressure, temperature, and volume changing with respect to each other. And in the first premise, we had removed volume out of the equation by maintaining it by having a fixed volume. In the second premise, we removed pressure out of the equation by maintaining a fixed pressure. Even temperature, we can do the same. We can also remove temperature out of the equation by maintaining the same temperature and just see how we can change the pressure. So if at all we maintained, I've not shown it here, but just a thought to note is that if we maintain temperature, if temperature becomes constant, all right? If temperature becomes constant, we will know that actually pressure and volume behave linearly. So now, linearly in this case, the proportionality is different. It's different in that pressure is proportional to 1 over volume. All right. But for temperature, we say that, for pressure and temperature, say that pressure is proportional to, pressure is proportional to temperature like that. But when it comes to volume with fixed temperature, we see that pressure is equals to 1 over volume. All right. Meaning when we increase pressure, volume does what? Volume reduces. All right. So if we have a container here, all right, with a fixed, where the temperature is the same, and then we apply a certain force to reduce the volume to that point, we'll see that the pressure here in this container will go up. So in this, we mathematically write it as pressure is proportional to 1 over volume. And from there, we are able to even say that pressure 1 and volume 1 should be equal to pressure 2 and volume 2. So this is another mathematical expression that I've not shown in the notes, but it's there. And I will see how it applies when we start looking at examples. So the last point that I just want to make before we go to start solving examples, in fact, even before that, I would like to find out if you guys are following and if I've not lost you anywhere. Are you guys still with me?
Yes, I am.
Okay, so Mr. Gilbert, you joined us late. I hope you'll be able to catch up. And yeah. So again, one of our friends, let me just help one of our friends again who's not able to hear us. Yeah. So, okay, she's able to hear, I'm sure. It showed that she was not able to. Okay, so now we are.
I can now get this. Was bad.
Oh, too bad, too bad. Okay, so now we continue on, just to talk about the last part. The last part that I want to talk about is that when we combine these premises, remember here we dealt with them individually. We dealt with pressure, temperature, and volume individually. When we combine the parameters together, what we find is that pressure and volume, all right, let me just write it somewhere here. We find that pressure and volume is proportional to temperature, all right? The product of pressure and volume is proportional to temperature. Now we want to find out the constant of proportionality. All right. The constant of, we are saying pressure and volume is constant to temperature. All right. Now to find out the constant of proportionality, this constant of proportionality is obtained by this expression. All right. We have this is the constant of proportionality is m over small m over big M. Now, what does small m over big M mean? The small m is the mass of the gas. For example, if they tell you that you have about 2 grams of oxygen, all right? If you have about 2 grams of oxygen, it will be given as this small m. And then you'll be asked to find a few things about this gas that you are told to calculate. So if you have been told that, for example, if you have been told that you have, for example, 2 grams of oxygen, how can you do your manipulation? How can you do your calculation? You must be also able to find out what the value of this M is, this big M. This big M stands for the atomic or the molecular mass. So if you know that oxygen always exists as O2. It doesn't exist as oxygen. So if you are finding the atomic mass, then you would know that you would need to find the mass of 2 oxygens, all right? 1 oxygen plus another oxygen, because we have 2 oxygens. So I suppose that you have the knowledge about mass numbers and whatnot in your chemistry. So we'll not talk about it in physics, but you would need to apply it. So if you don't know it, you have to revisit your chemistry. So I just want to talk about this constant of proportionality, that this constant of proportionality is this way. So now actually what we are going to do is I'm going to end this meeting right now. I want you guys to go back to the link so that you can join, so that we can finish up on the remaining part. Apparently it has taken us a long time to conclude on this matter, but I'm going to end this meeting. So you go back to the link and click it, you'll find me. Is that okay?
No problem.
Okay.
Yes.